Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we'll discuss the derivatives of trigonometric functions. Let's consider the derivative of sine x. By the definition of the derivative of sine x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. We expand sine of x plus h into sine x cosine h plus cosine x sine h, bring along our minus sine of x, and we have a denominator of h. Now we'll break it up into two pieces. We can take the sine x terms and pull them out, giving us the limit as h goes to 0 of sine of x times cosine of h minus 1 divided by h. And we have the cosine piece, the limit as h goes to 0 of cosine x times sine of h over h. Pulling out the sine x, since that doesn't depend on h, out of the limit, and the cosine x, that doesn't depend on h, we pull those out of the limit, giving us that the derivative of sine x is sine x times the limit as h goes to 0 of cosine of h minus 1 over h plus cosine of x times the limit as h goes to 0 of sine of h over h. Now we need to deal with these two limits. So the two limits we need to analyze are the limit as h goes to 0 of cosine of h minus 1 over h, and the limit as h goes to 0 of sine of h over h. We'll consider the second one first, and this is my favorite proof. Let's consider the circle of radius 1 on the right and these triangles inside. There's a red triangle and a red, green, blue combined triangle. That's a bigger one. And there's a sector of a circle made up by the red and the green triangles. Clearly, the red region is smaller than the red plus the green, and the red plus the green is smaller than all three colored regions together. So let's consider the area of each of those regions. Well, the red region is a triangle with base cosine theta and the height sine theta, since the radius of the circle is 1. And so that gives us an area of 1/2 base times height, 1/2 cosine theta times sine theta. The sector of the circle over here with angle theta, well, what fraction of the circle is that? That's theta divided by 2 pi of the whole circle. The area of the circle is pi r squared, in this case pi times 1 squared, and the fraction of the circle made up by the red and green pieces is theta over 2 pi times that pi 1 squared. So we have the area theta over 2 pi times 1 squared. The area of the large triangle, well, that has base 1 and the height is tan theta. So we get 1/2 1 times tan theta. Just copy that expression onto this page. Now we'll simplify, multiply by 2, getting rid of most of the denominators. Cancel out the pi, simplify the 1's, and write tan theta as sine theta over cosine theta. So we get cosine theta sine theta is less than theta is less than or equal to sine theta over cosine theta. Now we'll divide each of the pieces by sine theta. The first piece becomes cosine theta. The middle piece becomes theta over sine theta, and the right-hand piece just becomes 1 over cosine theta. I note that in dividing by sine theta, I'm assuming theta is positive and between 0 and pi over 2. That's all that we'll need here for our consideration. Now we could let theta go to 0. The left side, cosine of 0, well, that's 1. The right side becomes 1 over 1. So the left and the right become 1, and so theta over sine theta is squozen and must go to 1 as theta goes to 0. And therefore its reciprocal must go to 1 over 1, or also 1. Therefore the limit as theta goes to 0 of sine theta over theta is equal to 1. The other limit, the limit as h goes to 0 cosine of h minus 1 over h, well, in order to deal with that one, we multiply by the conjugate cosine of h plus 1 over cosine of h plus 1. The numerator becomes cosine squared of h minus 1. The denominator is just h times cosine of h plus 1. The numerator can now be written as minus sine squared of theta, right? We know that sine squared is equal to cosine squared. Sine squared is equal to 1 minus cosine squared, and therefore we have the numerator of minus sine squared of h. The denominator stays the same. We'll break up this numerator into a piece with just sine h over h, and what's left is another sine h over the cosine h plus 1. Well, we know now that the sine h over h goes to 1 as h goes to 0, and as h goes to 0, we have the other piece, the sine of h goes to 0, the denominator cosine of h plus 1 goes to 1 plus 1 or 2. So this first piece goes to 0. Second piece goes to 1. We get 0 times 1 is 0. So we can go back and find the derivative of sine of x. We had that the derivative was sine x times the limit as h goes to 0 of cosine of h minus 1 over h, which we now found is 0, plus cosine x times the limit as h goes to 0 of sine h over h, which goes to 1. And so we get sine x times 0 plus cosine x times 1. And we have the derivative of sine x is cosine x. We can use the definition of the derivative, the limits we've just derived, and the product and the quotient rule to find the trigonometric derivatives, many other trigonometric derivatives, including the derivative of cosine x, which is minus sine x, and the derivative of tan x, which is minus secant squared of x. Let's take a moment for some math and science culture. There was a foreign country in which a priest, a lawyer, and an engineer were about to be guillotined for their crimes. The priest puts his head on the block, they pull the rope, and nothing happens. So the priest declares that he's been saved by divine intervention. So he's let go. The lawyer is put on the block, and once again, the executioner pulls the rope, and it doesn't release the blade. The lawyer claims he cannot be executed twice for the same crime, and so he is set free too. They then grab the engineer, shove his head into the guillotine, and he looks up at the release mechanism and says, "Wait a minute, I see your problem." Thank you for joining us today. Have a great day, and may the power of math be with you.